2010 E&M number 1. They have given us an arc of charge. I think we did something very similar to this in the notes, except I think my example problem had a full semicircle. We might have done a quarter circle at some point, but here is a circle of arbitrary angle through which it turns. So it's distributed over, oh, they do tell us a quarter circle. That helps. And then they give us points A, B, and C. Notice that A and C are on the surface of the circle that would be outlined by this charge if it went all the way around the circle, and B is inside. This means that B is closer to the charge than A and C are equidistant, and they look like they're symmetric top and down also. Ooh, but they want voltages. So since voltages, we don't need to worry about vectors. Rank the magnitude of the electric potentials A, B, C from greatest to least, with number 1 being the greatest. Okay, so VB is the greatest because it is the closest, and then C and A are the same, so they both get 2. So we would be VB is greater than VA equals VC, and that's because B is closer and A and C are symmetrically equidistant. All right, now they're telling us point P is at the center. Determine an expression for the electric potential due to charge Q. All right, we're going to need some space for this. All right, so the electric potential is going to be the result of adding up all the potentials due to the little tiny charges dq that distance r away. Now the very nice thing about this circular arc is that as we walk along the charge, the radius is not going to change. So the radius is just going to turn into the radius of the circle. Now what we need to deal with here is the fact that our little tiny dq is spread out over an arc length ds. And let's see here. Oh, good. Uniformly distributed. That's important. So what that tells us is that dq spread out over ds is the same thing as q over the total arc length. Now they told us that it's a quarter circle. So S equals r theta, and a quarter circle would be pi over 2, and that's r, and that's S. So that means ds is now going to be r d theta. So let's get rid of the s's and put them in terms of r's and thetas. So dq over r d theta is going to be q over r pi over 2. We cancel out those guys, and now we can get rid of dq as 2q over pi, flipping that fraction around, d theta. Now let's go back to our original integral, because remember, we don't know how to integrate over charge, but we do know how to integrate over distance and angle and time, because angle is just a type of distance. So let's substitute everything back up into that integral, and we'll have k times 2 times q divided by pi, and this is radius squared, and then we'll have d theta. And what we need to also keep in mind is we're integrating over where the charge is, and the charge starts here and goes to there, so then that's a quarter circle, so we're going to go from 0 to pi over 2. And I'm not worrying about any sort of directions because voltage is directionless. So all of these guys are constants, and when we integrate this, we're going to get 2k q over pi r squared theta from 0 to pi over 2. Plugging in our limits, subtract 0, disappears, and then we have pi over 2, and hey, look at that, we got 2 over pi. So our voltage is going to be kq over the radius of the circle wait a second. Where did that squared come from? That squared does not belong there. Because that's not squared, this is voltage, not electric field. So you go away, you go away. Let's try this again, this time without the squared. So that's an R, and then this guy is just an R. I had it correct in my first one and then somehow turned it into an R squared. I don't know why I turned that into an R squared. So voltage KQ over R. All right, part C. A positive point charge Q with mass M placed at point P, released from rest. How fast is it going to be going? Okay, so for part C, what we have here is a conservation of energy problem. Original equals final. The original is going to be potential, and the final is going to be kinetic. The original potential is QV, and now we have a V derived, and at the end we will have 1/2 m other V squared. Keep in mind the first V on the left is voltage, and the second V on the right is velocity. And they want us to know how fast is it going to be going. So V is going to be 2Q capital V over M, all inside a square root. Now that we know what this big V is, we can plug that stuff in. And keep in mind, this big Q and that little q are not the same Q. So velocity is going to be 2K big Q, little q over M and big R. All of that will be inside the square root. Here's an expression for how fast the charge will be going when it's far away. All right, part D. I'm going to have to start scrolling down, which means my answers there need to go away, and there. Now let's scroll. Ooh, let's not confuse things with 2 yet. All right, part D. Dot representing indicate the electric field at point P due to the charge. Okay, so back up to our arc here. Since this is positive, all the electric field lines point away from the positive, and since this is symmetric top and bottom, the pointing down and the pointing up are going to cancel each other out, and the only thing that's going to survive is the electric field at, oh, they wanted this down here, this guy. There we go. The electric field at point P, it's going to point just to the right as the ups and the downs cancel each other out. Now, what this means is for part E, we're going to have to do some vector calculus. So let's delete or clear out everything from previous parts where we were finding the voltages, because that's really not that useful right now. And we're going to have to start over with the electric field expression. Unfortunately, we cannot use Gauss's law. We have to use the vector calculus version, which you could look up in your notes, or you could continue watching as I walk you through it one more time. So the electric field is going to be K dq over R squared, and we need to have an R hat here. And this is going to be from 0 electric field to the full electric field that's parallel to the axis, in this case directly to the right. So on the left side, we're going to end up with just the X part of the electric field, because the 2 Y parts, the part that comes from the upper half and the part that comes from the lower half, those 2 guys are going to cancel each other out. All right, dq. The dq we're going to deal with exactly the same way as we did last time. I suppose I shouldn't have deleted that. dq over r d theta is going to be total charge over r and then pi over 2. The r hat. Well, since we want just the right side part to survive, let's make that guy be the cosine piece. Let's see if I can draw. So this guy is going to be dE. from the little tiny charge here, dq. And we're going to compare it to that part, the right side part, because that's the part that we want to survive. So as we're making our triangle, draw this in blue here. So our triangle here, only the cosine piece survives, but since that means that the x-axis, this guy's going to be 0, and we're going to go down to minus pi over 4, and we're going to go up to positive pi over 4. And together that distance is going to be our pi over 2 quarter circle. So our r hat, in this case, is going to turn into a cosine. And we need to have a third thing. If you remember, there are 3 pieces of that integral that we need to take apart, analyze separately, and then put them back together. That third thing is going to be r. Fortunately, that's just going to be constant. So the little r squared is going to turn into the big R squared. Our integral then becomes something that is really not that evil. We can get rid of that guy. We're going to have 2k q over pi, and this time we're going to need to have r squared, and then we will integrate just the cosine piece, cosine theta, and don't forget this d theta here, d theta, and we're going to go from negative pi over 4 to pi over 4. All right, the integral of the cosine is the sine theta, and we're going to go from negative pi over 4 to pi over 4. Plugging those guys in, this is going to be 1 over root 2 minus negative 1 over root 2, which gets us 2 over root 2. And then don't forget our coefficient out front. So e sub x is going to be 2 root 2 k q over pi r squared. And I turned this just into root 2, because 2 over root 2 is just root 2. And this will be to the right, but again, we indicated that in part D.